Alrighty, so section 7.6 is about natural logarithms. And natural logarithms on the calculator, if they did it right, would look like that. And since that looks like the word in, on calculators they decided to use capital letters. So we've been using this button LOG here that's just to the left of the 7 button. LN is just to the left of the 4 button. And that's natural logarithm. So we're going to use that. And it's the inverse of, in the little blue right above it, you'll see e to the x. So if we need to undo e to the something, we're going to use natural logarithm to do that. And at this point, you kind of go, don't we know enough logarithms already? And the answer would be no, because this one is called the natural logarithm based on the fact that Euler's number is called the natural base. Now, the reason natural is in that name is because it happens in nature a lot. And so it's not just about the fact that Euler wanted to be a loan shark and charge interest all the time. It's also naturally occurring in our environment. If that's the case, well, then we have to know some math about it. So the natural base is e to the x, and the natural logarithm undoes it. So does that mess up all our rules, that if the bases are the same, that they'll cancel each other out? The answer is absolutely not, because even though natural log is written this way, this is what it really is. Made my e too big. Logarithm base e. So when we use it to solve, we're going to change it to logarithm base e. It's just written as ln because it's been around so long, hundreds of years BC. They were getting started on solving these things. And so somebody decided somewhere along the way that it would be ln that would stand for natural logarithm. And that's what they've used ever since. So today we're going to evaluate and simplify natural logarithmic expressions. We're going to start on this other objective, solve equations using natural logarithms. But to do that, we have to understand why this came to be. And here in the getting ready is a great example of that. Even though we're not going to do any graphing, it really helps us figure out what's going on with this graph. Oh, let's see, I'll move it up there a little bit. I don't like where that blue line is. A function f is said to be bounded above if there's some number b that f of x cannot exceed. So if there's a line you could draw above a graph and it's never going to get there, it's called bounded above. In fact, in pre-calculus we study bounded below as well. So if there's a line that you can say, hey, my graph's never going to cross this, then it's bounded below. In this case, they want us to figure out, is this bounded above? Does it stop going up at some point? Because it looks like it's kind of flattening out. Well, to know that, we need to know that the red one here is y equals e to the x. And we did study that one earlier. And here's what we found out. Pardon me. We found out we can put whatever x values we want into this one. So the domain is all real numbers. But not all the y's are going to come back at us, because our asymptote was the x-axis. So our y's were y is greater than 0. So now we're talking about its inverse. The blue graph, y equals the natural log of x. And we learned about inverses that what they do is they flip-flop the domain and the range. So the domain of natural log will be x is greater than 0. And the range will be all reals, because we have to flip-flop what we had for e to the x. Well, that tells me this is never going to stop going up, because the range is responsible for the y's, and that's going up and down, and it said it's all reals, so it's going to keep going forever. So this is, in a way, a proof, although it's algebraic and it's using graphing, that no, this doesn't have a lid on it. There's never going to be a cutoff for that graph. Now, that's to get us thinking e to the x we've already done. All we have to do is remember that ln is logarithm base e, and everything we've been doing works the same with this. So whether or not we're condensing, expanding, solving, everything we've learned about logarithms, we're going to do it again. And I love where this section is placed because then it gives us a nice review before we do the review for the test. Because we're going to follow the same rules that we have with all logarithms. So the function y equals e to the x does have an inverse. It is the natural logarithmic function. And the book is not going to write it as log base e of x. That's us. We have to know that. Just like we have to know log is base 10. We have to know that ln, natural logarithm, is base e. So when they say ln, most of the time we're going to change it to logarithm base e. So we can just use all the methods we've already learned. So our essential understanding is the functions y equals e to the x and y equals the natural log of x. They're both going to be functions. They'd pass the vertical line test. Just as before, this means that if a equals e to the b, then b equals the natural log of a, and vice versa. So if we snail shell it, it should work. So instead of writing it as b equals ln of a, I write it like this so it makes sense. When I snail shell this, this says e to the b equals a. And that's exactly what this says, right here. So we're taking something in logarithmic form, and we're snail shelling it, because the fancy name for snail shelling is exponentiating. So we're really exponentiating. Down here, they just show us, these are both things we could graph on a graphing calculator. And we'll see, yes, they are reflections in the line y equals x, which is exactly what inverses are supposed to be. So if y equals e to the x, then x equals logarithm base e of y, which is the natural log of y. The natural logarithmic function is the inverse of x equals the natural log of y. So we can rewrite it as y equals natural log of x. What are they getting at here? Here's what they're getting at. Remember, math is a secret language. And we've just learned something about what that says. Anybody want to take a guess what that really says? It says x. Because natural logarithm is logarithm base e. And when the bases match, they are pure inverses of each other. And we get x. Now, if that looked weird to you, try this one. What does that say? X. It says x, because this is e to the logarithm base e of x. These two cancel out, and we get x. So they're reminding us, even though it looks a little different, ln has a base of e, so it's going to undo e to a power. And again, logarithms are like perfect inverses. They just disappear. So we don't want to forget that piece. All right. Like I said, the great part of this is we're going to review a lot of skills that we need when we take the test next Monday, because a lot of this works exactly the same as the other logarithms we've done. So simplifying a natural logarithmic expression, what is 2 natural log of 15 minus natural log of 75 written as a single natural logarithm? I'm going to remind you, most books just say condense. Yours always says write as a single log, natural log, or a logarithm. So the first thing I do is I notice this 2 that's in front as multiplication. And I remember, oh, you're not supposed to multiply logs. That came from a power. That has to go back up here because the 2 is only in front of that term. So it's going to be the natural log of 15 squared minus natural log of 75. Do we know what 15 squared is? Easton? Subtraction in logarithm language. That's division. Don't suppose 75 goes nice and equally into 225, does it? How many times? There it is. Now, when we had numbers for bases, now I hate to say it that way because E is a number. Maybe we've forgotten that too. It's been a while since we did E. So if you want to see what E is, you can hit second division, and there's E. So E is a number. It's just kind of a weird number, you know, like pi. We've got a symbol for it. But in this case, normally we would stop and say, if I snail shell this, can I simplify this one? But if I did that, this would say e to the something equals 3. Unless you're a human calculator, I don't think you're going to be able to do that one in your noggin. So we just have to stop and say, done. All right, let's simplify some more. 1a, what is each expression written as a single natural logarithm? Do we have a power to put back up? Anybody know what 5 squared is? What's addition in logarithm language? So if you have 7 quarters, 175. Again, we don't at this point say, maybe I better try and simplify this. E to the something is 175. You know, it's E. It's too hard to do in your head. All right, take a look at B. Do we have power to put back up? A couple of them, right? All right, let's put them back up. Now the next step is where people make mistakes. The very next step here. They've got the x to the third, and then they write 2x squared. Why is that wrong? Both have to be squared. It was that entire term that had the 2 in front, so it's going to have to be 4x squared. That's a very common mistake. Alrighty, what is subtraction in logarithm language? Division. Can we simplify that? Take an x squared out of the top and the bottom, right? That's as simple as that's going to get. You know, we took it all the way down to natural log of x over 4. All right. C. Do we have powers to put back up? Well, let's do that first. And then we just have a string of addition. What's addition in logarithm language? Okay, then let's write it. And yeah, we usually put the 5 in front and then put the variables in alphabetical order. So there it is. Again, great review of what we learned in this chapter earlier about logarithms in general. You know, not just natural logs. Works that way for all the logs. Now, our objective had to do with solving. And that's a part of it, because just like when we solved logarithms before, sometimes you have to condense before you can solve. So we can use the inverse relationship between y equals the natural log of x and y equals e to the x to solve certain logarithmic and exponential equations. So Tell me what that says. Yep. So it's that inverse relationship. ln, logarithm base e, is going to undo e. And undoing e to a power, well, requires ln. So those two things go together, forwards and backwards. So now we're going to use that to solve. And there was no big box of step 1, step 2, step 3, because we know how to do this. We've done this before, just with different bases. So here we go. What are the solutions of natural log quantity x minus 3 squared equals 4? I don't know, it's got that goofy ln thing in there. Well, I know that's logarithm base e. And I know before, when we had logarithms and we were supposed to solve, we snail-shelled it. Well, we can do that here. It's just going to have a goofy e in it. E to the 4th equals x minus 3 squared. All right, so now I start thinking. Maybe I'm supposed to take x minus 3 times x minus 3 and get x squared minus 6x plus 9. Oh, buggers. Then I'd have to subtract e to the 4th, and I'd have to factor with e. You think we're supposed to factor with e? That does not sound like fun. So instead, I notice, hey, these are both even powers, and they're kind of high. I'd rather have smaller. Well, I could take the square root of both of those, and that'll take care of that. So square root, and we want to put the plus or minus on the left-hand side. It can go on either of the two sides, but students like it better when it's over here. And then the square root of e to the 4th is e squared. There's more work if you put the plus or minus on the right-hand side, so students really like this one. It's a little easier. Almost done getting x by itself. All I have to do is add 3 to both sides. And then it's going to be calculator time. I mean, these are definitely going to be our 4 decimal place problems here. So we need 3 plus e squared and 3 minus e squared. And there they are. 10.3891 with rounding. And negative 4.3891. So now I get a little nervous. Because remember, negative answers, not always a good idea. So I started thinking, well, let's see, if I do put this negative in here this time, whatever I get in here has to be squared. So it's still going to be positive anyway. So I don't have to worry. They're both going to be positive. You definitely could check them. You know, we have ln on our calculator, so you could just punch them back in again and check that they both work. But because I see it's going to be squared and it's going to be positive, I'll wait for a simpler one for us to check it. All right. And here comes the simpler one right here. Natural log of x equals 2. How should I write that? Easton. Base e, snail shell it. Cool. Let's find e squared. 7.3891. Now, because this one is definitely much easier to punch in, all I'd have to do is check the natural log of that. So, natural log of the answer I just had up there And there it is. It's 2, which is the other side. So definitely works. Alrighty. B has a little bit more meat to it. What should we do first? Snail shell, but I need a base. So this one's really similar to the first example I did up there. So what do you think we should do next? Yeah, definitely. They're both even. Let's get it down to where it's workable. So plus or minus e squared equals 3x plus 5. Well, now it just looks like algebra. So what do we do next? What else? And then we grab our handy-dandy calculator. Oh, let's see. Parentheses 5 plus second e squared, parentheses. Oops, got to pop it out of there. Divided by 3. And then I'm going to cheat and do second enter and just change this to a minus instead of having to punch it all in again. So there they are, 4.1297. And negative 0.7964. Double check that one. 7964, yep. So that one took a little bit more, but mostly algebra. And then we're using the calculator. Oh, let's see, can I fit this one in here? I think I can. Alrighty, problem. I can't snail shell that one right away, since it's not condensed. So help me out. How do we condense that? We do. Now, is it ready to snail shell? With what base? Yeah. One more step before we punched in. What's that step? Exactly. E squared. Oh, let me try and punch it in at one time. Second e squared, boom, divided by 6. 1.2315. Again, checkable. Now, if you want to use your rounded answer, it'll get you close to the value. Like if we were to punch this one in with 4.1297, it'd get close to 2, but it wouldn't be perfectly 2. If we use the answer that's stored in the calculator, then we'll perfectly get a 2. That's as far as I wanted to go today. So we get a little practice with this whole E business. Got a good start on our objectives. And this little assignment, we'll put it in your brain